Hello everybody. In this video I'm going to take us through the calculations for Part A and Part B, Trial 1 for our Eudiometry Lab. So I'm going to start off by calculating the actual number of moles of calcium carbonate based on the mass. And so I'm taking the mass that we were given in our student data, and I'm dividing that by the molecular weight of calcium carbonate that I would have gotten by adding up the atomic masses of 1 calcium, 1 carbon, and 3 oxygens. So it's going to be 100.09 grams per mole. I cancel my grams. I get 1 over moles, or moles, and I get this many moles. Next, we have our equation for the pressure of the CO2. This is going to be our equation for that. And we're going to calculate each of these terms kind of individually down here. So we're going to start off with P column. This is the density of the water times G times the height of the water column. I showed you where we can look up the density based on the temperature. For trial 1 it was 25 degrees Celsius. But what I did is I went ahead and I converted this to kilograms per meter cubed because I need to do that for the units to all work out. So we had grams per milliliter. There's 1,000 grams in every 1 kilogram. There's 1,000 milliliters in every liter, and there's 1,000 liters in every cubic meter. So I'd like you guys to go through and do that conversion for yourselves to prove to yourself that you're going to wind up moving the decimal place 3 times here. So it's going to be, there are 1,000 kilograms per meter cubed in every 1 gram per milliliter. I'm going to multiply by 9.8. This is just a constant. It's the acceleration due to gravity at Earth's surface. So that's always going to be 1 standard value. It has units of meters per second squared. And then I'm going to multiply by the column height. It was given to you in the student data as 46 centimeters, but I need that in meters. So I converted that to 0.46 meters. When I cancel my units here, I'm canceling these meters with 2 of the meters in the denominator here, and the units I wind up coming up with are kilograms per meter times second squared. This is equal to a Pascal. So when I multiply these all together, I get, and I have 2 significant figures there, so I got 4,500 pascals or 4.5 kilopascals. When I go to my table and I look up the vapor pressure of water at 25 degrees Celsius, I get 23.8 torr. I'm going to use this conversion factor that there's 101.4 kilopascals for every 760 torr, and I see that that's 3.18 kilopascals. I come back up to this equation. I was given the pressure of the atmosphere in our student data. It's going to be this value. We're going to be using that for every time that we use the pressure of the atmosphere. We're going to subtract from that our 3.18 kilopascals and our 4.5 kilopascals from there, and we get that the pressure of the CO2 is equal to 95.88 kilopascals. Next, we want to calculate the number of moles of calcium carbonate that was reacted. We're going to do that by rearranging our ideal gas law here for N, and we get PV divided by R and T. I plugged in the pressure of the CO2 here in kilopascals. I have the volume. This again was given to us in the student data, but it was given as 28.9 milliliters. I converted that to liters. And I also converted our temperature of 25 degrees Celsius way up here to 298.15 Kelvin. I did that so that I can use this R value here, 8.314 liters times kilopascals per mole Kelvin. I can now cancel my kilopascals, cancel my liters, cancel the Kelvin. I again get 1 over moles, and I get this many moles of reacted calcium carbonate. I take my N reacted moles and I divide it by my N actual moles that I got up here. I multiply that by 100% and I get 98.9% yield. Now you're going to do this for 2 more trials, and you're going to average together your percent yields to carry forward to part B. I am just going to carry forward this value to part B because I didn't do the other 2 trials here. In part B, we start off very much like we did in part A. We're going to calculate the pressure of the column, density times gravity times the height. Now, I have the same density as I used before, but this is only because of a coincidence, okay? Part B, trial 1, was done at the same temperature as part A, trial 1. When the trial's temperature changes, you're going to need to look up a new density and convert that again to kilograms per meter cubed. So this value will not always be the same for every trial. I'm going to multiply that by G, which will remain the same. And I'm going to multiply it again by the height in meters of the water column for that trial. I get 6,830 pascals, or 6.83 kilopascals. Again, the temperature was the same, so I'm just carrying forward the pressure of water. But for other trials where the temperature is different, you'll need to go look up the pressure of water for that temperature and make a conversion there to kilopascals. When I plug this in for my pressure of CO2 equation, I get the pressure of the atmosphere minus the pressure of the water minus the pressure from the column. I have 93.55 kilopascals. I'm going to go ahead and calculate my number of moles of calcium carbonate, just as I did before with the PV over RT. And again, I'm going to convert this to liters and this to Kelvin. And again, for other trials where this is going to be a different temperature, you're going to need to input a different temperature there, and you'll have a different volume for the various trials as well. And I find that we have this many moles of calcium carbonate. I'm then going to use the equation that I spelled out in the book to convert the numbers of reacted calcium carbonate to the number of moles of actual calcium carbonate by dividing by the percent yield and multiplying by 100%. I've just written that as dividing by the yield, and I'm dividing by 0.989 because 98.9% as a decimal is going to be 0.989. And after making that little correction, I get this many moles of calcium carbonate. I'd also like to mention that what we're doing up here to get the pressure of CO2 is we're making corrections to the atmospheric pressure, right? And we can see that between the pressure of the water and the pressure of the column, we got about 10-ish if we add those two numbers together, right? This number is about 100. So if we weren't making those corrections, we would wind up with somewhere just under 10% error. So we can see that it is important that we made these two corrections to this when we're doing this. Now we have the mass of the calcium carbonate. This is going to be those N actual moles that we just calculated times the molecular weight of the calcium carbonate, which we know to be 100.09 grams per mole. And we get this many grams of calcium carbonate. Finally, we're going to take that mass of calcium carbonate and divide it by the mass of the sample, times that by 100%. When we do those calculations, we can see that out of our sample, 50.1% of it was calcium carbonate. And because we have a binary mixture of calcium carbonate and sodium chloride, we would know that 49.9% of it was sodium chloride. You're going to do this for trial 2 and 3 for part B. You're going to average those together to give me the final percent mass.